Hello, welcome to my calculus video. In this video, I'll be teaching limits, derivatives, and integrals. In later videos, I'll teach sequences and series, and parametric equations. Now let's get started with limits, what everything else is based on. The best way to describe a limit is a function approaching a number without reaching it, being arbitrarily close. Here is the notation for limits. The x is the variable we are controlling, c is a constant and is what we're trying to approach, and the f of x is the argument or expression inside the limit. This reads, the limit of f of x as x approaches c is equal to L. One way to understand how to use limits is to see them graphically. A hole is where there is a single point missing in a line. A break is where two parts of a line don't connect. An asymptote is where a line extends beyond the graph to positive or negative infinity. You can use limits to prove that a function does or does not contain discontinuities. A function that does not have any discontinuities is called continuous. Limits can also be denoted approaching from a specific side, left or right. From the right notation has a small plus sign, and from the left notation has a small minus sign. It is also common to find the limit of a function as x approaches infinity or negative infinity. You can do all basic operations inside a limit. The limit is either a value or it does not exist, denoted d and e. If it tends toward infinity, it is technically d and e, but it's common to say that the limit tends towards positive infinity or negative infinity. Another way for a limit not to exist is if it is an alternating sequence or function. The way to find what the limit is, first plug in the number. If it has a determinable value, that is what the limit is equal to. If that doesn't work, you can apply known limits. If that doesn't work, you can try to see graphically if it approaches a value. There's also L'Hopital's rule, which can help solve limits. This is, when there is a 0 over 0, its limit is equal to the derivative of the numerator over the derivative of the denominator. Stay tuned to learn about derivatives. A derivative is the slope of the tangent line at a single point. If we look at the equation to find the slope of the line, we see the slope is equal to y2 minus y1 divided by x2 minus x1. This finds the average rate of change, or slope, between 2 points. For a function like f of x is equal to 2x, if you find the slope at any point, you'll get a slope of 2, and the tangent line will be parallel to the function line. However, for a function like f of x is equal to x squared, then the slope changes depending on the value of x. So this equation is just an approximation. However, we can use the slope formula as well as limits to find the instantaneous rate of change at a single point. If we set the difference between x2 and x1 to be a new variable, h, it rearranges the equation. Then if we set h to be arbitrarily close to 0, we get the limit as h approaches 0 of f of x plus h minus f of x divided by h. To find the instantaneous slope of x squared, we can't just plug in because it would be 0 in the denominator, but the x plus h can be distributed through the function. After factoring out the h over h, you result in the limit as h approaches 0 of 2x plus h. You can now plug in, and you get the result of 2x. So now we know that the instantaneous slope at any point of x squared is equal to 2x. This is the definition of a derivative. There are many helpful rules when taking derivatives, but I won't walk you through the proof of every single one. A derivative of a function is a new function that describes the rate of change of the old function. This can be used for many applications. If many variables are dependent on each other, the rates are also dependent on each other. For example, if there is a rectangle and its width is 40 meters, growing at 2 meters per second, and its length is 60 meters, growing at 3 meters per second, and you want to find how fast the area is growing, first, take the derivative of the area with respect to time, and you get dA dt is equal to w times dL dt plus L times dWt. After you plug in what you have, you get dA dt is equal to 240 meters squared per second. These types of problems can get very complicated, but the ways to solve them remain the same. There's also the antiderivative, also known as an integral, that can be applied to functions. It involves adding up all of the values of a function or finding the area of a function. When there are straight lines, this is not too difficult. We can just use geometry to find the area. But when the functions are curved, a new strategy must be used. We can approximate the area using what are called Riemann sums. Essentially, you fill up the area you want to calculate with rectangles. The width is a repeated specified value, and the height is the value of the function. But we can use limits again to find the exact value. By filling it with approximately infinite rectangles, the calculated area is infinitely close to the actual area. And this can be written as an integral. Integrals can be definite, meaning that they have bounds and are equal to a value, or indefinite, meaning that they are a general antiderivative and are equal to a function. It is important to remember that derivatives and integrals are inverse operations. So a derivative of an integral is equal to the original function. But also, whenever you take a derivative, some information is lost, because any added constant can be ignored when finding slope. So you have to make up for this by adding back an unknown constant whenever you integrate. This is just an arbitrary constant and can absorb any non-variable operations. There are many strategies to finding integrals, like u-substitution, integration by parts, trig integration, trig substitution, method of partial fractions, improper integrals, and unbounded integrals. When integrating, it is useful to memorize common integrals like these. U-substitution involves substituting u for x in an integral and also replacing certain parts to change it into changing with respect to u instead of x. It only works if the derivative of one part of the integral is equal to another part. Let's do an example. With the integral of x squared times e to the x cubed dx, first, set u equal to a part of the equation. Then take the derivative of both sides, so you can substitute dx for du. When choosing which part of the equation to substitute with u, choose the one that looks like it has a derivative elsewhere in the function. Then in the integral, substitute x and dx for u and du, and if possible, solve. Now, you can substitute x back in, and you'll have completed the integral. Sometimes you may have to u-sub multiple times to continue simplifying an integral, and you'll need to keep track of all your substitutions for when you substitute back to x. Here is the formula for integration by parts. The integral of u dv is equal to u times v minus the integral of v du. You will separate the integral into two parts, choosing one to be u and the other to be dv. Then you'll need to take the derivative of u to find du, and integrate dv to find v. Then just substitute back as shown in the formula. Here's an example. Sometimes you will have to repeat this process, which brings up tabular integration. For an expression like the integral of t squared times e to the t dt, you could repeat integration by parts until you have solved it. Or, you could set up a table with the u, dv, and plus or minus. You take the derivative of the left row, integrate the middle row, and alternate plus and minus for the right row. Then combine along the diagonal once a column equals 0. For this to work, there's an order of priority that you must follow, called Lipit. Logs, inverse trig, polynomials, exponentials, then trigonometry. And these are what you should choose to be u. Also, here are the inverse trig derivatives that you might need to use. Next is trig integrals, the strategy used when you need to integrate sine and cosine, but u-substitution doesn't work. You'll be using these trig identities. For stuff like this, you can just use u-substitution and set u equal to the function to the first power. However, for integrations like this, it doesn't work. This is where you need to use trig identities until u-substitution is possible. For the integral of cosine cubed x, first change it to cosine times 1 minus sine squared x dx. And then you can integrate it easily. For cosine x to the 6th times sine x to the 5th, you reorder sine x to the 5th, like so, and then substitute in to 1 minus cosine squared. Then you can use u-substitution after this. You can use this technique, substituting sine x squared is equal to 1 minus cosine x squared, or cosine x squared is equal to 1 minus sine x squared, when sine or cosine are both to an odd power. But when they are both even, you'll need to use a slightly different technique that use the half angle identities. Here's an example. You may need to use the technique multiple times to solve it. Remember to attempt using u-substitution before using this technique, as it will simplify it a lot. Next is trig substitution. Right now we can solve for something like this, or something like this, but we can't solve either of these two things. For these we will need trig substitution. We'll substitute x for a trig function and then use trig identities to help solve. Here's a table of what to substitute when. Here is an example walkthrough for the integral of 1 over x squared times the square root of x squared plus 4 dx. First, we determine what substitution to use and find its derivative. Then we find what the square root is equal to, and then we substitute those in and simplify using trig. For this integral, we also have to use u-substitution. Now, once we have solved the integral in terms of theta, we will use our knowledge of trig to find what we need to substitute back to x. I'd like to use this triangle and populate it using our initial substitution. Then, using the triangle, determine what you need, in this case, sine theta. Substitute it in, and you will have solved the integral. There are some cases where there is a lone theta, so your final answer will have inverse trig in it. Next is method of partial fractions, which is a technique used to integrate rational functions, like f of x over g of x, where f and g are polynomials, and the degree of f is less than the degree of g, and it is a proper fraction. We note how to combine fractions to a single fraction. For example, 3 over x minus 1 plus 2 over x plus 2 is equal to 5x plus 4 divided by x minus 1 times x plus 2. Partial fraction work in reverse. The denominator, once factored, may have any of the following. A factor is linear or irreducible, and a factor is distinct or repeated. A note: if f over g is not a proper fraction, first you need to rewrite using long division. After doing so, the last term will be a proper fraction, and the method of partial fractions can now be used on it. To find the coefficients, multiply both sides by the denominator, and then plug in values for x. First use values of x that will zero out the factors, and then try to use simple values. We'll often have to solve a system of equations to figure out each coefficient. I recommend practicing this technique to better understand the process. Next is improper integrals, and the limit of integration are infinity. Here are the rules on how to determine if they converge or diverge. Similar to improper integrals are unbounded integrals, where the domain includes an asymptote. Here are the rules. Thank you for watching.